Hi everyone, here's your week 9 video on nuclear radiation. This corresponds to unit 6A and 6B from your book. Today our focus is going to be a review of the structure of the atom, so what that means for protons, neutrons, and electrons, a review of isotopes, and then relating that to radioactivity and what is a radioisotope. We're going to look at average atomic mass. We're going to compare ionizing and non-ionizing radiation and the effects and how we use that for detecting and measuring ionizing radiation. And we're going to look at the difference between alpha, beta, and gamma radiation and their effects on living tissue. And then in part B, you're going to be working a little bit more on the different types of radiation as well. And for part C, you're going to be working on a little bit of background radiation information. So first, let's review what's inside the nucleus. There's a lot going on in this slide, but this should all be review for you. If we take a boron atom, so here's our little glimpse, our little square from the periodic table. It has the atomic number 5, which tells us that there's 5 protons in the nucleus, and it has a mass of about 10.811. That's a weighted average mass dependent on the number of isotopes that are out in nature. So that's going to tell us how many neutrons are there. So in this example, there's 6 neutrons. So this isotope is boron 11. So it has a mass of 11. It has 5 protons and 6 neutrons, which adds up to 11. And then you can see the orbitals, the energy levels to show where the electrons are. So remember, inside the nucleus, you have the protons. They're positively charged. The atomic number tells you how many protons there are. They identify the element. That's their major influence and purpose. And they have a mass of 1 AMU, so relative mass of 1 atomic mass unit. Neutrons are neutral, so they have no charge. Their main job or descriptor is that they stabilize the nucleus. They allow there to be space between the positive protons inside the nucleus and allows all of the protons to be able to be stable and near each other. Again, that mass number, that number 11, is the protons plus the neutrons. And when I move the cursor, it should show up over there. And then again, over here, remember the electrons are actually outside of the nucleus. They're not in the nucleus at all, and they are negatively charged. They determine reactivity as their main contribution, and they have a no relative mass. So their mass is considered so little that it doesn't impact the mass of the whole atom, and their mass is negligible. So what's an isotope? If you have atoms of the same element and they have the same number of protons, but their number of neutrons is different, they're considered an isotope. And because neutrons also have mass, when that number of neutrons changes, the mass number changes as well. So we have examples here. Again, this is boron. We have protons, there's 5 protons. In this example on the left, there's only 5 neutrons, which makes a mass number of 10. 5 protons plus 5 neutrons gives you a mass of 10. On the example to the right, you have 5 protons but 6 neutrons. That adds up to give a mass of 11. Notice there's 5 electrons in both. They're both neutral atoms, but the electrons do not contribute to the mass. These are 2 examples of stable isotopes. What if an isotope is unstable? And that's what we're going to continue with on the next slide. A little reminder is the atomic mass on the periodic table is the weighted average that is dependent on the abundance of the naturally occurring isotopes. So what I mean by abundance is how common they are. So if one isotope is more abundant or more common than another one in nature, the weighted average is going to be closer to the mass of the common one. And that's why the numbers aren't necessarily a mean where you add the numbers and just divide. It's not like that. It's considered weighted, just like your grade is weighted in our class. So with that, unstable isotopes, they are considered radioisotopes. They are radioactive isotopes of an element, and that means because their nucleus has an unstable combination of neutrons and protons, and they have excess energy in their nucleus. Examples of radioactive isotopes or radioisotopes are hydrogen-3, which is tritium, carbon-14, chlorine-36, and lead-210. Remember, we write this as the element name, then the dash, and then the number is the mass number. And that mass number, I'm going to repeat this a lot, is the protons plus the neutrons. It's important. So what's radioactive decay? Radioactive decay is when those unstable nuclei spontaneously break down and it releases that excess energy and some matter, in some cases, from the nucleus. So there's going to be a release of particles and or energy. There's always a release of energy, but in 2 cases, there's release of particle as well. Well, for the 3 that we're going to talk about. So there's a gamma ray, which is strictly energy. And then there's an alpha particle, which the particle is like a helium particle. We're going to talk a lot about that. And there's also energy release. Or a beta particle, which is similar to an electron and energy released. So they all release energy. Remember, a radioisotope is an unstable nuclei. They have a really hard time staying together. The decay won't stop until all the unstable isotopes are transformed into stable isotopes through this radioactive decay. Unlike chemical reactions, nuclear reactions are not affected by changes in temperature, pressure, or the presence of catalysts like we learned last week. Also, nuclear reactions of a given radioisotope can't be slowed down, sped up, or stopped. There's 2 types of radiation overall. There's non-ionizing radiation, which has lower energy, and ionizing radiation, which has higher energy. Non-ionizing includes infrared, microwaves, visible light, radio waves. These forms radiation transfer energy to matter. They make molecules vibrate, and electrons move to higher energy levels to heat up. They're generally safe, but overexposure can be harmful. So you can see that sunburned person is overexposure. That's when it can become harmful. And then there's examples of them there. On the other hand, ionizing radiation has much higher energy. They can eject electrons from atoms and molecules. It causes ions and free radicals to form. This can damage cells, particularly the proteins and the nucleic acids, which you might remember from biology are incredibly important in your biological development. This could give an inability to heal, birth defects, cancer, radiation poisoning. And this could come from UV radiation, gamma rays, X-rays, and any type of nuclear radiation. So we use a couple different methods to detect radiation. We use Geiger counters, we use scintillation counters, we use film badges. They each have a little bit different purpose. A Geiger counter, if you expose the Geiger counter to radiation, a current will flow through the device, and then it can detect alpha, beta, or gamma radiation. First developed in the 1930s. That's this picture here, this top one. The scintillation counter is the one that is down here on the bottom right, and that produces a bright flash of light, or scintillation. So it flashes light. And when that's exposed to radiation, the flashing starts. It's a little bit more precise than a Geiger counter. And then you have a film badge, and these kind of look familiar. You might have seen people wear those. They wear them on the job. What happens is radiation passes through several filters within this device, and it goes through a transparent area and strikes a film. And different amounts of radiation can pass through each area, and what shows up on the film is the radiation that's kind of present, and it gives you more information about it. We use this to monitor the degree of exposure, but it doesn't protect you from exposure at all. And really all of these, none of these are going to protect you from exposure. They just let you know if the exposure exists. They just detect it. So we can use radiation for a variety of things. So in museums, we use it to analyze matter. You can use it to detect art forgeries. So fake art. Crime labs can use it to analyze gunpowder residues. You can use tracers in agriculture to see the effects of herbicides, pesticides, and fertilizers on plants. You can use it to use radioisotopes to diagnose medical problems. There's 3 examples there and what medical problem they can diagnose. And then we've used radioactive isotopes to treat diseases like cancer and thyroid disease. So there's 3 particles. There's an alpha particle, there's 2 particles. There's an alpha particle and there's a beta particle. We're also going to talk about gamma rays. There's other particles as well that can be emitted, but we're going to focus on these 3. And if you go into further chemistry classes, you'll learn all about the positron and other examples, and the neutron. So we've got alpha particles and beta particles are particles, and gamma rays, there's no particle there, it's just energy. So first, an alpha particle. An alpha particle is composed of 2 protons, 2 neutrons, and has a 2+ charge. So it's essentially a helium nucleus. So we can use 2 symbols. We can use the alpha symbol, which is kind of like a curvy A, and we can use a helium symbol. Now, the 2 down here represents the 2 protons, kind of like an atomic number would, and the 4 up here represents the mass. Since it has 2 protons and 2 neutrons, and they all have mass, that's your 4 AMU for the mass. This is the largest of the 3 main types of nuclear decay particles. Its penetrating power is pretty weak. It can be stopped by paper or skin. However, if you inhale alpha radiation or ingest alpha radiation, it can be very damaging. Alpha particles are often produced when atoms with an atomic number greater than 83 decay. So you're looking at, on the periodic table, greater than 83. So 83 is right here. And so anything after 83 in that row and below it is when you would see alpha radiation. And here's an example of an equation here, and we're going to look at equations in part B. A beta particle is really a fast-moving electron that's emitted from the nucleus. It's an electron, so it has a -1 charge. Its symbol is written as an E for electron, or the beta symbol. It has a mass of 0, and the atomic number, or the number of protons, is affected by -1. And we are going to talk about that in a second, but this is the symbol that we use for that. These are 8,000 times smaller than alpha, and it leads to greater penetrating power. They can be stopped by heavy clothing. During beta decay, a neutron will actually decay to produce a proton and electron. And the proton stays in the nucleus, but the electron gets ejected. So that's where you get that decay of an electron. That's the particle that's being emitted. And then the neutron's going to be turning into a proton. And there's an example there at the bottom. So here's showing that in a symbol what this is saying. And here's an example of beta radiation in a chemical equation. And the last one we're going to talk about is gamma rays. They're very high energy, but they have no mass. They have no charge. So their symbol is the gamma symbol, and 0 mass and 0 for the number of protons. They have the most penetrating power. They can be stopped by several feet of concrete or lead, but they're the least damaging because it's not really found naturally in our atmosphere. It's found more in space. And here's a visual to kind of help you see the penetrating power. So alpha is stopped by paper. Beta will go through the paper, but can stop by a hand. Gamma can go through paper, through a hand, through water, but it's stopped through layers of concrete. And then a neutron, which is one we didn't talk about, can go through paper in your hand, but can be stopped through water. So it just kind of goes over the penetrating power. So let's review. For atomic structure, protons are positive, neutrons are no charge, and electrons are negative. Protons give the atom its identity, neutrons give it stability, and electrons determine reactivity. Isotopes are the same element, but they have different atomic or different mass numbers. They have radioisotopes, are unstable isotopes, so they have an unstable nucleus that has excess energy. The combination of neutrons and protons is unstable. The average atomic mass will depend on the naturally occurring isotopes and how many of each you have, and it's a weighted average. For radiation, we have lower energy radiation, we call ionizing radiation, and non-ionizing radiation, which is higher energy. And for nuclear emissions, we have alpha, beta, and gamma. So an alpha is positive, it's a particle, it's the most massive, and it's the least penetrating power. Beta is also a particle, but it has a negative charge, there's no mass, has a stronger penetrating power. And gamma, it's a ray, it's only energy, there's no mass, it has the strongest of the 3 penetrating power. It's least harmful to us because it doesn't exist near here. So hopefully this helps. When it gets to the chemical equations, we're going to go through all of that in part B. So if there's still some questions about that, hang tight. Part B will help you with those. And otherwise, send questions my way. Have a great week, everyone.